snap before. So I finally, and somebody mentioned to me they were having a little trouble. So it turns out there were all sorts of interesting things I learned. So let me tell you kind of this story. So first off, in the old days with PIC parts, there was our current program header has several things involved. Okay. And one of the things, so it's got some pins that have to be connected, and it takes up some of the ports. All right, so our current, if you have a PIC-Kit 3, R4, or the ICD3 or 4, you have basically a 6-pin header, and those pins are there's a little arrow on one of them. There's a little arrow on one of them, and that's pin 1. And that pin goes to the master clear. Okay? And then you have power, ground, and then you have the clock, so it's the debug clock, and then you have the debug data. And then you have one pin that's not connected. Okay? That's the 1, 2, 3, 4, 5, 6 pins. Now, the snap has 8 pins. So that in itself is a little confusing. But the first 6 pins are the same, or the first 5 pins are the same. Master clear, power, ground, clock, and data. Now, the PIC-Kit has the ability to power the board, but the snap does not. Okay? The PIC-Kit has the ability to program the board in a standalone manner. You can download the code into the PIC, and then you can program multiple parts by punching one of the buttons on it. We haven't ever used that, but you can do that with the PIC. With the snap, you can't do that. But here's the big difference. So in the old days, we had another pin that was involved in this interface, and it was called, I think it was called PGM or something like that. Nowadays, as the parts evolved, this program pin went away. And so now the standard in-circuit serial programming and in-circuit debug interface is this interface. Now, what happened back in the day when we had this program, there's two different ways to program the device. High voltage and low voltage. Okay, high and low voltage. Okay, so it's embarrassing when an electrical engineer can't spell voltage, but that's how it is. All right, so anyway, so we have high and low voltage. In the old days, the high voltage was actually like 14 volts. It was pretty high. Nowadays, it's I think 3 volts over VCC or something. I don't know. It's not that high. But and the low voltage programming didn't exist initially, and then they introduced it. Well, there was a period of time where when we had these programming pins, that if you set it for low voltage programming and you powered up the chip and the program pin was not connected to anything and it floated, it could put the chip into a funny mode where you couldn't program it at all. And so for that reason, the advice was made to set low voltage programming to off unless you were going to really use it. So that's kind of what I've always, I sort of saw that someplace, and that's just been in the back of my mind. So without really giving it much thought, I just always used the PIC-Kit 3, and we set the configuration bit in the configuration words for low voltage programming off. Well, it turns out the snap uses low voltage programming. It also turns out that when the programming pin was taken out of the processor line, so the new ones don't even have that pin, that problem went away with the chip locking up if you had the low voltage programming bit programmed for off. So now it's better to go ahead and just program it for low voltage and do it in low voltage. There's really no problem with that. The PIC-Kit can do either one, but the snap can only program in low voltage. So because of that, when they ship these parts, they always ship them with the configuration bits by default on the chip. The low voltage programming bit is shipped in the off mode. And so that way you can, if you have a brand new chip, you can program it with a snap. But if you have programmed your chip with a Picket 3 with the low voltage programming turned off and not on, then you can't program it with the snap. You have to go back and program it again with the Picket 3 and set the configuration bit for low voltage programming to on. And then you can program it with the snap. Okay, so I didn't know that, and that was news to me, but that's how it works. So when you buy a snap, it's fine, it works great, it's faster than the Picket 3, but you must, if you've already programmed it once with our standard configuration word, where the low voltage program I told you to set it to off, now you have to go back, set that bit to on, program it with a Picket 3 to on with any program, and then the next time you program it, you can program it with the snap. But if you try and program with the snap and it's already been programmed with the configuration word where the low voltage program was turned off, which was the default thing we've been using, then it won't program the part. It'll give you that error and tell you that the low voltage programming bit has to be programmed on. And oh, by the way, you can't do that with the snap because the snap can't program it when that bit's off, so it can't fix the problem. So that's a little bit of a pain in the butt, but that's how it is. So I do encourage you, otherwise the snap's a great thing, and it's a lot cheaper than the Picket 3, which they've discontinued anyway. And it programs faster, it has most of the same features, but a few of them it is missing. And the two that are missing, it can't power the board, so you need to have your battery, or you need to have a little USB cable with the 2.5 millimeter plug changed, put on the end of it so you can power your board. And if you want, I'll give you one of those plugs so you can modify your, find an old mouse, cut off the cord, dig out the red and the black wires, and then connect them to that 2.5 header. You can take your existing header, feed that wire through, and have it set up so you can either put a battery on it, or you can plug in the USB port to your computer. But do not plug it into your computer and have the battery on at the same time, because then you'll blow your USB port on your computer. But you can have a dual use cord where you can connect either power source to it and have the same plug work for your board. Anyway, I recommend you get that set up. Okay, so that's one thing. So anyway, and so I finally got my snap fired up and figured out what the problems were. But if you've already programmed your board, you need to borrow somebody's Picket 3 and program it, go into the configuration word, turn on low voltage programming and program it again, and then now you can take your snap and program whatever you want in it. And as a result, I'm going to recommend that you use low voltage programming on, even with the Picket 3 now. It'll work just fine, and it doesn't have the problems that it used to have with some of the legacy parts, because the new parts don't have that pin even. So there was a time when it was always desirable to avoid low voltage programming if you could. Now that is no longer true. And I think it's also true when you use the chip in bootloader mode, you also have to have the low voltage programming turned on. Okay, any questions about that? No? Good, okay. So that's one thing. Now the second thing, so I want to show you the little demo. Anyway, this semester is kicking my butt a little bit. We have this new EPICS thing going on, and I've got, essentially, instead of my normal 3 courses, I have 5 courses. So it's driving me crazy. Yes, but anyway, but it's good. It's also kind of fun. All right, so let me fire this up. So I want to show you the PWM mode. And so if you look at the syllabus, so what we're supposed to do today is so if we go to spring 19, 63 syllabus. So here on the 21st, project instructions, finish the A, and then finish A to D, D to A, UART, and the demo A to D and the UART. So I'll do that, and I'll talk about those as well. I do want to talk about the project. So the first thing I want to talk about, so tonight when I get home, one of the things I will do before tomorrow, before midnight hopefully, I will create a project group tab in Blackboard, and I will set it up so you can have 1, 2, or 3 people in your project group. So assuming that we get the date approved, on the It's in the syllabus. Well, here, it's in the syllabus. So let's see. Yeah, the 11th. So on the 11th of April, that Thursday, we're going to have a mini demo where you'll have half of a table and half of a bulletin board, and you'll be able to set up your little project and show it. And we'll have judges go around, and there'll be a couple $100 in prize money for first, second, and third places that's split up. And it's an opportunity for you to kind of, you know, show your stuff to some of the other students. It's kind of nice, and it's actually fun. Did any of you see that last fall or last spring? Okay, so you know kind of what that looks like. And then I think on the 23rd, we'll have the Micro 2 class will race their cars and demonstrate their tilt tables. So that'll come up a little bit later. And now, if we don't get those dates, it might move. I asked Justin on Monday to get them for us, and I haven't heard, so I don't know. But in any event, hopefully we'll have the atrium. It'll be in the atrium of the BSC, and so hopefully you'll be able to do that. Okay, so the project is a requirement for the course, and it counts for 25% of your grade. I grade it pretty lovingly, so if you just do a reasonable job, you'll get something in the 90s for sure. Question?
Can we ask you for help if we're ever stuck in a situation?
Oh, absolutely. I've spent hours and hours helping students with their projects, and I sort of enjoy it, so it's not a big deal. And I do have some suggestions for you too. You don't have to go out and buy parts. I mean, if you can, if you want, because most of the things we want to interface are cheap. I think on the web you can pay, I don't know, $12 or $13 and get 45 different peripherals you can interface to the Arduino or to a PIC. So you can always do that. But whatever you need, I have plenty of them. And I have GPS. I have pH meters. I have pH probes. You do the meter. I have all sorts of LCD displays, OLED displays, on and on and on. You name it. Accelerometers. 9 degree of freedom, IMUs, you name it. So we've got a whole bunch of things, and so I'll go over those in detail. But what I want you to do before next Tuesday is to decide how you're going to do this team-wise. You can do it all by yourself if you want, although I think you can do that if you want. But I encourage you to work with other folks. You can have 1 or 2 partners. So a group of 3 is the maximum size. And here's the rule. You can, when you do your initial proposal, you can do it with 1, 2, or 3. That's fine. And I'll show you, there's a link online, I'll turn on, and you can submit your proposal online. I'll review your proposal, and as long as what you're proposing is reasonable, you're fine. You do have to have either an interface to an external device or using an internal module for each of the members in your group. So if you have 3 people, you have to do something a little more complicated than if you just have yourself. On the other hand, most of the people who do projects by themselves do more complicated projects than some of the groups. So generally, usually that's not a problem. And I count GPIO pins as one module. Okay, so you do have to have a little more of a complicated project if you have 3 people, but it's not that big of a deal. And we've had some people that have really done some cool projects. It's really a nice thing to put on your resume and your job app and that sort of thing. So it's kind of a fun thing to do, and I think most students really do enjoy it. Some students go for the least they can get by with. So I'll review your proposal, and as long as I approve it, that's fine. But I may tell you that you need to do something a little more. What I don't want you to do is do something that's just a lab, exactly like one of our labs. So it has to be a little more than the lab. But you can take the same things we do in lab and combine them together with a little more, a little fancier software. So like one of the things students frequently do is they use the touchpad. So as you know, there are 4 touchpads on the board, UTSA, and you can set up a sequence of events to turn your board into a cipher lock. And you can have it so you can hold the button down and put in the code, and then you can then without the button down, you have to put in the right code to open the lock, and if you put in the wrong code, then the lock won't open. And you can drive the lock with the 2 transistor switch and the little green terminal block, so you can actually drive a relay that actually drives a real lock, or you can just simulate it with LEDs or whatever. So that's one that a lot of people do. And what's interesting in that one is, you wouldn't necessarily realize this, but the user interface is a big deal. It turns out, and that's one of the really important things you need to learn from this. When you're trying to write an application for an embedded controller that, you know, Joe Blow house person is going to use, you have to make it so that it actually works with the average person. And if your interface is so complicated and goofy, so it doesn't make any sense, and people, you know, would have to read a 20-page manual to figure out how to make it work, that's not a very good user interface. You've all used bad user interfaces and good user interfaces. This is your chance to write a good user interface. Oh, guess what? It's actually hard to do that. It takes a lot of code. It takes a lot of code to debounce the buttons, to make sure that the reasonable amount of time between pushes is there, but not too much time required, so that it becomes awkward and painful and too slow, and on and on and on. And you'll find when you're taking the touch buttons, it's great if you just want to sense is it touched or not. But when you want to sense multiple touches to put in, you know, touch 1, touch 2, touch 3, touch 4, and maybe even the same button twice in a row to count for 2 touches, and you're trying to write the code to keep that from being 100 touches or 0 touches, you'll find it's actually challenging. It's actually somewhat complicated. So what looks like it could be a simple project, if you do a really nice user interface, so that as you play with it, you go, yeah, that works great. That's going to count for a lot. So it's not just how many modules you manage to tack on. It's also the quality of the code you write, and whether it's robust and it works, or whether it, you know, it only works every 10th time you do it, blah, blah, blah. So the first thing I want you to do is you know, organize, get together your group, and then go on Blackboard and using the group feature, and you'll see there'll be a button that'll pop up when I turn that on. Register as one of the groups. And I think I'll create enough for like up to maybe 30, maybe 40 groups, 36 groups, something like that. I guess I'll do 40 groups, but we probably won't have 40. We'll probably have 31 or 32 or something. And again, feel free, 1, 2, or 3 people. Now, once you submit your proposal, and you should put on there the names of all the people in your group, only 1 proposal per group. So if you have 3 people, don't submit the same proposal 3 times, just 1 person submits it once. So decide among yourselves, if you have 3 people, who's going to submit it. And then I'll make sure everybody gets credit for it. So every group needs to submit a proposal, whether it's a group of 1 or 2 or 3. Once you submit your proposal, you can kick people off of your group, but you can't add people. So if you have a group of 2 and then there's somebody, you know, the day before demo day wants to be added to your group, no, you can't do that. In fact, you can't add people once you submit your original proposal. And the reason for that is there's always somebody that doesn't want to do anything, and then they sort of goad their friends into letting them be part of their group, even though they didn't do anything, and get credit for it. And so we're not going to do that. If you want to be part of the group, you have to be part of the group from the get-go, which means you're going to have to do some work. If your friends want to let you coast for the entire time, that's fine. But we're not going to come cap in hand at the last minute and have somebody feel sorry for you. Okay, so you can put now, as far as the proposal goes, you can modify the details of your proposal extensively. And in fact, I may require you to do that in some cases. I may say, no, it's not complicated enough, or, oh, it's way too complicated, we need to scale this down. I'm not going to prohibit you from doing something complicated, but I am going to recommend you back off if it looks like there's no way you're going to get that done. Okay, so by next Tuesday, at the end of class, I want everybody to be locked in a group. Okay, so try and get that sorted out over the weekend, tomorrow, Monday, over the weekend, and then on Tuesday, make sure you've entered that in Blackboard by class time if you can. You don't have to submit the proposal right away, but I want you to do the group thing. And like I say, I'll set that up tonight. Okay, any questions about the project? I'll go over a lot more details of all the options you can have, and I'll talk through a bunch of stuff. I'll talk about some of the previous things. If I can find my video, I'll show you some video. And I don't know, a lot of options. But we had one group did a hoverboard with their pick. They actually had an accelerometer and they controlled powerful DC motors on the hoverboard, all with the little pick. It can do some amazing things. Now you can also use, you know, we do have fancier computers out there. You do have to use your board. Or if you have 3 in the team, you can use one of the 3 boards. Or you can use all 3 of them if you want. But what you can't do is use an Arduino for your project. We're not doing that. We're using the pick. All right. Any questions about projects? We're good? All right. Okay, so let me set some wires up here. Okay, so I'll plug some things in. I've got about, I feel like Mr. Gadget or something. Okay, so let me say a couple of things. Well, so I'm going to do the demo and then I'm going to talk about some of the hardware with the slides. So, so let me switch to, well, let me switch to the document. So one of the things, okay, so one of the things, so this is the snap, in case you haven't seen the snap. And you can buy it, so I think we're charging $10 for the snap and $2 for the little cable. And so when it's plugged in and working, well, it's plugged in and stuff, power, the green light comes on, and when it has data and stuff, and it's talking to the pick, this red light comes on. And when you plug it in, you'll notice there's a little arrow on the side here. You probably can't see that, but we can focus down. So you see the little arrow right there? That's the first pin. So when you connect it, that has to go over here on that side, like this. So it kind of sticks over a little bit past the, like that. So it should be, so the 2 pins not used should be kind of tucked behind the analog socket there, okay? And then when we use the UARTs, so here's the UART. Now, the way this is designed, and if you want to, I'm willing to sell you one of these if you want. You can buy it and just have it permanently mounted here. And you can actually power your board through this too. So if you compare the pin out here to the UART, you have to plug it in such a way that the pins line up, which actually is like this. But if you put right angle pins like this and they come out the top, you can put it on like this. Okay? And when it's sending data, you'll see the little red LED on it lights up, and it's actually flashing real bright, but it's flashing too fast, you can't really see it. And then I also plug the potentiometer in here, and the way this is working, it's going to read the potentiometer, it's going to write out the value of the potentiometer through the UART cable, and then it's also going to write the value of the potentiometer into the duty cycle register for the PWM, and the PWM is set up to drive the blue color on the LED, and the other colors have been turned off with this particular code. And I'm not going to go through the code in too much detail because you've got it in lab. And it's actually a little bit of a pain in the butt. But, all right, so the first thing, so in order to use a UART, you have to set up a terminal program. So the one I've been using lately mostly is one called PuTTY, just because it's free and it works okay. It's not perfect, it has some limitations. There's plenty of terminal programs out there. In the old days, we used them all the time because when we tried to connect our phone lines, we always work through a terminal program. The idea of having you know, something like Firefox or Chrome or Edge or Netscape Navigator or any of the other thousands of browsers out there. We didn't have any browsers. We just had terminal programs. That's all we had. Does anybody remember those days? Probably not. I think we're all too young. It's disgusting. Anyway, I hate to say it, you guys missed out on the good days. What can I say? But it's okay. It's pretty exciting now, though, I will say. Technology-wise, we're at the greatest moment in history that I've ever seen. Unfortunately, there's a lot of things about life right now that kind of suck. We seem to have a lot of stupid people trying to do a lot of stupid things. Okay, anyway, and you know, with any luck, we probably won't be blown up by communist China for another 10 or 15 years. So, okay, so you go into the device manager, and I'm going to plug in this CP2102 device that I plugged into my board. My board's all set up for it, and which is really nice. The boards that we used to use, so the third generation boards had a whole bunch of headers on them, but we kind of learned we didn't really use most of those headers, so we took them all off except for the UART header and the analog header. But you can still get all the same pins from these dual row 10-pin headers that are there that connect every pin. But the dedicated headers for special functions, we just have the UART header and the programming header and the analog header. That's it. I think it works better. It opened up space so we could have four touch buttons, and I don't know. Anyway, it's better, I think. So, as you see on this, I have the Silicon Labs CP210X USB to UART bridge on COM14. And some computers, when you plug it in a certain USB port, it always instantiates with the same COM number. And then other boards, they change the frickin' COM number every time. So you really have to check, depending on your computer. And then the Snap programmer is here on COM4. And you could actually open up a COM link for that too, I think, but I'm not going to do that because it might interfere with my IDE. But in any event, I think you can actually work through that as well, interestingly enough. All right, so here's our CP2102, and it's on COM14. So I'll shrink this down. And now I'm going to run PuTTY. So here's PuTTY. I'm going to click Serial. I'm going to set the speed at 9600 baud, which is its default value, and I'm going to put 14 in. And now it's going to open up this window. And it's a little spastic, but basically it's showing me the pot value. And you can see over here on the setup, I take this potentiometer, which has the two white wires connected to VCC and ground, and the black wires is plugged into RA4. And RA4 is set up as an analog input, and it's connected to the A to D, and the A to D is converting the voltage that I'm picking between VDD and VSS. I'm currently running it at 3.3 volts. So the max voltage is 3.3 volts, and the minimum voltage is ground. The max voltage will give me a full 10-bit count of all ones. So that would be 1024, and the zero voltage, the ground voltage, should give me 0, or something very close to it. So if I take the little pot and I change it here, and you can see I'm going up. So now it says 1023, and then I go all the way down, and it goes down to 1. So I don't get 0, but I get 1, and every value in between. Okay. Now what I do in my software, I'm going to take that value I'm reading from the potentiometer, and I'm going to write that value out to the duty cycle register in the PWM module. And so I'm writing, in this case, all the PWM modules have a CCP RXL and a CCP RXH register. And I'm using CCP module 3, so it's CCP R3L. So that's what I'm writing it to. And I write that value in there, and then it uses that to set the brightness. Now, the interesting thing, it's a little screwy, but you can see now it's 1023, and if I click over to the document camera, you can see that my LED is, well, I don't know if you can see it. It's fast enough that it fuses the signal so that I'm not seeing a lot of blinking. Then it looks like it's on a steady value, and it's flying. It's plenty fast. But as I turn my pot, as I turn my pot, well, remember, when the pin sends a 1 out, then that's when it's off. So in this case, I'm sending out something close to 1023, so it turns the blue LED off. And if I sent out 0, it would turn it maximally on. So as I decrease the value on the pot by turning it, you can see that the blue LED gets brighter and brighter. And then at that point, it's full brightness, and I'm down to a pot value of 1, basically. And you can see it's refreshing. The green's kind of irritating. If we had a nicer terminal program or a fancy GUI, we could avoid that, I guess. Okay, so I'm reading the pot. I'm writing it out to the PWM module as the duty cycle in the duty cycle register, and I'm also printing it out through the UART so I can see it on this terminal program on my computer. So that's a perfect example of several things going on at the same time, and sometimes along with that I might use one of the other colors of the LED to blink every now and then to tell me if things are working, and I can use that to help debug the code, and I can also obviously single step through it. What's interesting is the PWM module takes care of writing that recurring signal out to the PWM port. All I do is write the duty cycle value in the register. So I can change this. If I put it, say, at 512 or something like that, it should be at about half brightness. And you can kind of see, that's kind of what it is. It's about half bright, and then as I go down. But the nice thing is I have pretty good control over it to make it go pretty much the full range of values here. And I can have very, very low levels of it. Because, again, even though the LED is completely non-linear, as I give it either full voltage or no voltage for different percentages of my pulse repetition cycle, I can pretty much fully control the brightness and the amount of energy I'm delivering to that LED. So that's why PWM is so nice. And it's also a great way to control a bunch of other things too. If I wanted to do a servo, which maybe I'll probably show you that next week, all I'd have to do is slow the pulse repetition frequency down so that it's about 50 hertz instead of what it is now, probably quite a bit faster. Okay, all right. I think that's pretty much what I wanted to show you. So we will cover all the functionality in the lab. So you're gonna go through how these work. And as you do these things in the lab, you want to pay attention so that if you want to use, like if you want to have a terminal program when you set up your project, and in fact, just to debug things, sometimes it's really nice to have the terminal program set up so you can write some values out to the screen as the code's running. And if you format it nicely, you can see it. You can see it like this, where it's where you can read the value as the program's executing it on the fly. It's kind of nice. You can also use all the debug features in the integrated development environment. Between all that, it really is, it makes it pretty easy to find out what's not working in your program. Okay, so let me bring up this. Okay, so there's several things I wanted to do. So let me talk about the A to D just a little bit. So that's one thing I wanted to cover. And I'm having trouble remembering what I covered and what I haven't already. But so here's the A to D. Okay, so this is a block diagram of your chip. And you can see we have the CPU here where we crunch all the instructions and we do all the math. We have random access memory out here on the data bus along with all the peripheral modules. And that's because we have memory mapped I/O on this chip. On your desktop or laptop, your computer memory sits completely elsewhere, has its own separate address and data bus, and has nothing to do with the I/O bus where all your peripherals sit. But in this chip, it's all the same because it's memory mapped, which is really as it should be. And then, because it's a Harvard machine, we also have program memory sitting out here on a separate bus, 14 bits wide of data, a bigger address bus, 15 bits of address bus, 14 bits of a data bus. Here we have 8-bit data bus and only a 12-bit address bus. The upper 5 bits come from the BSR, lower 7 come from the instruction when you're direct addressing, and then if you're using indirect addressing, you get 15 bits from, or 16 bits from the indirect registers, of which you only use, well, it's mapped in different ways, but you only need 12 at the end. And then you have some clock generation modules and your debug stuff and a bunch of other things. All right, so there's the CPU. Notice here you have your 10-bit A to C module down there. And you have timer 0, 1, 2, 4, and 6. You have comparators. You have your 4 PWM modules, your eCCP1 and eCCP2, and CCP3 and 4 modules. These are enhanced CCPs, and these are just regular old CCPs. But for purposes of PWM, we can use them as single-ended where they behave in the same way. But if you want to use a full bridge or a half bridge, you can use 1 or 2. And then we have this master synchronous serial ports, which is the SPI and the I2C. We have 2 of those. And we have the UART. There's the UART. And so we're using the UART, we're using the 10-bit ADC, and we're using CCP3 in this particular program. And you can use, and some of these ports are also being used as part of the data moving in and out of these modules. Sometimes we'll use these ports just as GPIO ports, but sometimes these modules will commandeer those ports and use them for their own purposes. In the case of the ADC, you can have up to 12 of the input pins can be analog inputs. And so we'll look at this, how this works. So here's our block diagram of our analog to digital converter. Now, we have, these are the external pins, and then interestingly, there are even some internal connections that don't connect off the chip, but they connect the modules inside the chip. And we can select any of these 12 pins for inputs, and they're numbered AN0 through AN11. But they don't correlate directly, they correlate directly with the various pins, but they don't go in any kind of ordered fashion. So AN0 happens to be RA0, and AN1 happens to be AN1, and AN2 happens to be AN2. But AN3 is actually A4, and then AN4 is I think C1 or 2 or 0 or something. So you have to actually go to the manual. You have to go and look up in the manual and see what pin is actually connected to what port. And you find that information in the data sheet. So we go to the data sheet, down here someplace. Right there. And we go down to the A to D module, down here someplace. So the A to D, D to A, so I start on the D to A and back up, and that gives me the fastest way to get to it. So here are the modules. The channel select is in the analog digital. So there are 2 control modules for this analog A to D converter. Many microprocessors have many channels associated and very complicated ones. And the PIC line, even parts in this same family, have much more complicated A to Ds than this one. This is a fairly simple A to D without a bunch of the complicated circuit that you can find. And anyway, AD-Con 0 and AD-Con 1. Con 0 has the number that picks the channel you're connecting to, and then there's a go done bit and there's a AD-On bit. The go done bit starts the conversion, and the AD-On bit turns on the module. So you have to have the AD-On bit set, but when you select the channel, if you change from one channel to another and select a new channel, you have to wait a small amount of time before you turn the go done bit. You cannot do it in the same instruction, because if you do, the capacitor that I'll show you in a second, the very small value capacitor that samples your signal, doesn't have time to sample it. It won't fully charge up. Even though it's a very low value capacitance, it still takes a certain finite amount of time. It takes a few microseconds to charge up. And as a result, if you write this all in one fell swoop, it'll pick a new channel, but it won't have a chance to have the capacitor represent the actual voltage on the pin at that instant. And so you'll get meaningless data. All right, so if we go to that register and we look at it, you can see that here's how the bits are laid out. Upper bit's not used. Then you have 1, 2, 3, 4, 5 channel bits. And then you have a go done bit and an 80 ohm bit. So these 5 channel bits are laid out here. So AN0 is 0, AN1 is 1, 2 is 2, 3 is 3, 4 is 4, and all the way to 11. Then there's nothing on the bits between here and here. And then finally, at whatever this is, 11101, that's the on-chip temperature sensor. And that can actually give you the temperature of your die and tell you, and if it's not particularly hot, it'll probably give you something close to room temperature. On the other hand, if you're really working it hard and it's a little warmed up, it'll be a few degrees warmer than room temperature. And then you can also monitor your digital output converter, your DAC output. So that's your digital to analog converter. That takes a digital signal and generates an analog voltage, whereas the A to D takes an analog signal and generates a digital word. Okay, so this DAC output here is only 5 bits, so it only has 32 different voltages it can display, which with proper filtering gives you, not a very good signal, and certainly not good enough for audio of any high fidelity audio. Normally we like to do 16 bits for high fidelity audio, so we're quite a few short. And then finally, the 1F is the fixed voltage reference output. So inside the chip, you have a module called the fixed voltage reference, and you can select, depending on what voltage you're running the chip at, 4.048, 2.024, or 1.0. Let's see, I didn't do that right. 1.024, 2.048, or 4.096. So you can select those 3 choices. But if your maximum voltage is, say, 3.3 volts, then the 4.096 selection is not available to you, because that's in excess of the voltage you're providing the chip. So you can't do that one. But you can do the lower 2. And those are nice to use. You can actually use those as a reference voltage for your A to D converter if you want. Or you can use it for something else. Or you can send it out a pin so that but you can internally check it if you want to. Anyway, these are your options. And then, of course, we always want the A to D to be on when we're going to use it. And then when we're ready to do a conversion, we set the go done bit. So first we select the channel and make sure it's on. Wait a few microseconds, and then we set the 8 on bit and start a conversion. We pull on this bit, and when it's cleared, we know the conversion's complete, and we can read the conversion in 2 registers. Now those 2 registers are ADCON 1 configured. And ADCON 1 configures our output registers with this 1 bit, this called ADFM, AD format. And what ADFM does, it either right justifies or left justifies an unsigned 10-bit value. And that unsigned 10-bit value then represents the conversion. And it should read from 0 to 1024. 1024 if we're at VCC, 0 if we're at 0. And you can see with the pot, it works pretty close to that. It's pretty good. And then we have two bits that select or 3 bits that select our positive, 3 bits that select the clock we're going to use with this module, and 1 bit for our negative reference, 2 bits for our positive reference, and those are the options. So the options for the clock, FOS divided by 2, FOS divided by 8, FOS divided by 32. this FRC clock supplied from a dedicated RC oscillator that allows the A to D converter to work when the chip's completely asleep and the FOS is stopped. And then FOS divided by 4, 16 or 64, and I guess there's 2 FRC selections for some reason. And then you have the negative reference. It's either the ground on the chip, VSS, or it's an external pin. But even if you use the external pin, you must still keep the voltage range for your A to D conversion between VSS and VDD. Whatever VDD you're running your chip at, that's the maximum voltage you can A to D. Anything above that's just going to give you the maximum count. And if you go too far above it, you may cause problems. So you don't want to do that. And if you go too far below the negative, the ground, in the negative voltages, you'll get into trouble too. You may burn up your chip. So you want to be careful with that. So your only 2 choices are the chip ground or an external reference that's above ground. Now, why would you want to have a tighter range on your A to D converter? Well, the answer is, let's say, normally when we have, let's say we have some external device over here. Let's say it's a sensor. And it could be measuring air temperature, humidity. It could be measuring the strength of a GPS signal. It could be measuring the amount of water in the soil. It could be measuring all sorts of stuff. So, but it's generating a voltage, and now we want to convert that voltage into information that our microprocessor can process and make decisions on. Like, is it above a certain threshold, below a certain, within a desirable range? It could be a water level in a tank, or a liquid level in a gasoline tank or something. So you get this sensor, and this information comes out of the sensor, and it goes to your microprocessor. Well, here's the problem. So let's say your micro is running on 0 and 3.3 volts, okay? But let's say this sensor is going 0 to 5. Well, now we have a problem. Once we get above 3.3, we're gonna clip the rest of our signal off, and it's always gonna read max. So we need to scale this between this. We want to scale this 0 to 5 voltage to 0 to 3.3. So what we do is we put an op amp in here, and then our op amp. And typically, what we do, we have it set up so that we give a little bit of feedback, and this defines the gain. And then we have a little bit of a voltage divider here. And this defines the offset. And so we pick these resistances so that we get this op amp to condition this signal to put it in exactly the range we want, to be 0 to 3.3 with the proper offset. Sometimes our sensor generates a signal plus or minus 1 volt. Okay, so it goes from minus 1 volt to plus 1 volt. And so when you have that sort of a signal, you need your DC offset to add 1 volt to the signal, so that now the signal goes between 0 volts and 2 volts, with 1 being the center point of the signal. And so often you have to condition your A to D inputs with an op amp. Now, some of the microprocessors in this family have built-in op amps inside the die, so you can just use those. But in many cases, you'd still have a problem, because even inside the die, they're restricted to the 5 volts. And they can't take the negative signal. So sometimes that doesn't really help you. Usually you have to. So make sure when you're doing your analog coursework that you do learn how to use op amps, because they're very critical in interfacing analog signals to our D-to-A converters. And remember also that your op amp has slew rate limitations. So if you have a very high-speed signal, you need to make sure your op amp matches your signal. And if you have a very high speed, if you need a big bandwidth, you need to make sure your microprocessor can handle the bandwidth you need. Most microprocessors are somewhat limited, and so sometimes what we'll do is we'll have a standalone A to D module that will actually feed this in, and then we'll feed that in to the microprocessor on a digital line. So this will actually do the conversion here, and then send in a digital signal instead of using an internal A to D converter in the module. So there's all sorts of features. you can certainly save money if you don't need, if you don't need real high bandwidth. But if you have to have something like video, well, oftentimes for video you're going to have some pre-processing because our micros may not be fast enough. Although some of them are, some of them will definitely handle video no problem. But anyway, very high speed, gigahertz signals that have to be demodulated. Well, we might have to have a separate module for that. Okay. Any questions about how that's set up? So those are the two configuration words you have to do. They're pretty straightforward. You just have to remember this mapping from the analog pin to the actual pin is kind of complicated. Where do you find that information? Well, okay, so that information you go back up here to the diagram that lays everything out. And here it is. For our 20-pin device, we just look at the A to D channels. So notice, here's how they're assigned. RA0, AN0, RA1, AN1, RA2, AN2, RA4, AN3, RB4, AN10, RB5, AN11, RC0, AN4, RC1, AN5, RC2, AN6, RC3, AN7, RC6, AN8, RC7, AN9. So you can see they don't necessarily follow any logic organization. They kind of do, but it's scattered around. So you have to refer to this pin allocation table for your 20-pin part in order to make any sense out of this at all. Okay? So here's the AN numbers, but here's the RA numbers. Now if you look on the little board, we put both the AN number and the RC number on the little silk screen on your board. It's hard to read on mine because that red kind of screws it up, but you can see it's there. Can you see the letters there? So ground, power, and then RC2, AN3. No, AN6, RC3, AN7, and RB5, AN11. So it's AN6, 7, and 11 is what's on your analog header. And there's reasons for that. Some of the other analog pins aren't as available that we're using those. Maybe we're using those other analog pins for the UTSA letters up here. Different things. So just keep in mind, there's reasons why we didn't do anything. And then of course, RA0 and RA1, RA0 and RA1 already have, they're already tied up with your Picket3 header or your snap. So you're using those for programming purposes. You can still populate them within your project. You can use those pins, but you just have to remember you have to be very careful when you use them because you have to make sure you're not screwing up the pin when you're trying to program the part. So what you have to do is put jumpers on or something so that you don't plug in whatever it is you're using that pin for until after you've programmed the part. And then you can, but then that takes away some of your debug capability. So if you possibly can, you should avoid using RA0 and RA1 in your project because they are dedicated to your debug header. So if you want to be able to use any debug features, you've got to avoid that. But if you're going to program and forget, then you could use it. It's just that you can't use the debug. Okay. All right. So that's what this looks like. Now so these switches indicate how your 1-bit selection on your negative reference, your 2-bit selection on your positive reference. There's actually only 3 choices, so the 4th choice is not used. And then this all goes down into this ADC module here. And here's the go done bit that starts the process. Here is the multiplexer that picks which channel you're going to connect to the A to D module. Now, notice what kind of a multiplexer is this? Is this a standard digital multiplexer? Where you put in a 0 or 1, you get a 1 or a 0 out? It can't be, right? It has to transmit an analog voltage. So this is actually an analog switch. It's an analog multiplexer. So it actually takes the voltage level on this pin and faithfully transmits it through whichever one's selected. That one's connected to this ADC module. So that's an analog multiplexer, not a digital. It does have this 5 bits of digital input to determine which channel is selected. So it's actually a mixed signal device. It's got digital signals and analog signals both. But the signals coming in here are all analog voltages, and you're getting an analog voltage out, and it's selected digitally. Okay? So that's your analog multiplexer. Here are the switch. Here's your settings for your positive voltage and your positive reference and your negative reference. Notice this, if you connect it up here to the 1, then your negative reference is generated by the input on pin AN0, which is RA0. Well, that's problematic because you're using that for your header, for your debug module. And then your positive reference comes in on AN1. So we generally don't use these external reference pins. You could use them, but you have to connect them after you program the part. So you program the part, then you would put the chip on the board or solder these references into place, or you would put jumpers on or something. All right, here's the little conversion module right here, and it generates a 10-bit output that is either left or right justified and stuck into two 8-bit registers. So the overall output is 16 bits, but of course 6 of those bits don't have any data in them. And it's you either have the upper 8 bits or data. If it's left justified, the upper 8 bits are here, and the lower 2 bits are the upper 2 bits of the lower register with 4 bits down here that don't do anything. Or if it's right justified, it's slid this way, same thing. You have the 2 upper bits up here and the lower and the low 8 bits down here. Anyway, that's how this is set up. So this is the AD on switch. So this turns on this powers the module, and here's the go down signal. Now, this module here it's what's called a selective a SAR, a selective a sequential I forgot SAR sequential. Well, I'll tell you how it works. I forget what the SAR means. But anyway, so I think I've said all this. So here's your SAR, Successive Approximation Register. That's what it is. Okay, so here's how this works. It's very straightforward. So here's your analog signal coming in on the other side of your analog multiplexer. And it's connected to this sample and hold capacitor. Again, a very small value capacitor. I forget what it is. It says in the data sheet. But it's some picofarads, okay? Maybe even less. A few picofarads, I think. Anyway, so your signal's connected to this capacitor, and it charges up, and that the capacitance, this sample and capacitor, will follow your input signal, pretty much. And with some small lag due to its time constant, because it does take a little bit of finite time to charge, but it's pretty fast. And you can definitely, 8 of these signals, probably, well, I don't know, maybe as fast as a kilohertz. That may be about all you can do with this, but you can probably do a kilohertz without too much trouble. Maybe 2 kilohertz, but that's probably it. All right. So anyway, so you're sampling the signal, and then when you hit the go done switch, here you hit the go done switch. What it does is it disconnects this capacitor from the input and connects it to this comparator. Now this comparator is just a type of op-amp, and the comparator has very, very high impedance inputs. So even though this is a very small value capacitor, it doesn't get drained. The voltage on it doesn't change appreciably when it's driving this comparator, because the comparator has such high impedance inputs, almost zero current is flowing. And on the other side, we have this successive approximation register driving a DAC, a digital to analog converter. And interestingly, even though the DAC on our chip is only 5 bits, this DAC is 10 bits. And all 10 bits then are used to generate, we have a 10-bit register here that sends the 10 digital bits into the DAC, and the DAC generates an output voltage proportional to the value of the SAR. So the way this works, we have some value in the SAR register, and that's going to be divided by 1024. So if the SAR register is 1024, then it's going to be times the VDD, okay? In this case, 3.3 volts, or 5, or whatever you set it at. And that's the voltage that's going to appear on this other input down here on the comparator. And then there's going to be an error signal generated, and it's going to go back to this successive approximation. The high order bit, this is important. So it always starts, all the A to B conversions start with the high order bit. And when it does, it sets all the other bits in the SAR to 0, and it sets the high order bit to a 1. Now, if we have this successive approximation register then goes into a DAC, so if I have a 10-bit DAC, okay, a 10-bit DAC, and I set that 10-bit DAC to 1 0 0 0 0 0 0 0 0 0. Okay, what's the voltage that the digital to analog converters that's connected to my SAR register? What's the voltage it's going to output? Well, it's going to output. Essentially, it's going to output this over 1 1 1 1 1 1 1 1 1 1. Okay, and since this is something like 512, and the other is 1024, it's going to be 512, so 1024 times my maximum voltage of 3.3. So that's actually going to look a lot like 1/2 of 3.3, which is what, 15 plus 1.5, so 1.65, right? So it's going to actually send out 1.65 volts to my comparator. And then my sampling capacitor is driving the other input, so it represents my signal voltage. And if my signal voltage is greater than the DAC voltage coming out off the SAR, then I will leave that higher order bit set, and I'll set the next bit. But if it's lower, I'll clear the higher order bit and set the next bit. And the process repeats. So at each level, I set the bit, check the comparator, and if my DAC is high, I clear the bit. If my DAC is low, I leave it set and set the next bit. And I walk down through all 10 bits till I get to the last bit, and then I do the same with the last bit. I either leave it set or clear, depending on whether it's higher or lower. If it's lower, I'll leave it set. If it's higher, I clear it. And I'm done. Which means I'm down to plus or minus the least significant bit representing my signal. So what's the accuracy? Well, the accuracy is plus or minus 1 10/24 times 3.3 volts. That's my accuracy. And now, assuming there's no noise in the system and everything is working just like it should. Usually there is a little noise, so you probably have a little jitter, but it's close. And so I'm going to be plus or minus about 1 10/24 of 3.3 volts if I'm running at 3.3 volts. Whatever that is, it's not much. It's definitely down a few microvolts. I don't know, somebody can pop up their calculator and do that. So 1 divided by times 3.3. So it's 0.00322246. Now, why do you think, this is a nice little tidbit, it took me 70 some odd years to learn. Why do you think that our fixed voltage reference is 1024, 2048, and 4096? It works out that if you take 1 10/24 of 1024, it's a nice even, it's not a non-terminating fraction. It's a nice, so it would be, 1/24 of 1.024. So it's basically, these effectively cancel, and it's 10 to the minus 1, 2, 3. So it's 1 times 10 to the minus 3, or 1 millivolt. Right? Or, yeah, I think that's right. 1 millivolt or a microvolt, I forget. But anyway. So it's a nice even, it comes out nice and evenly. So they use powers of 2 in these fixed voltage references for purposes of making your A to D values nice and clean. So if you want to clean up your A to D values, that's one way to do it, but you don't have to. It's not a big deal. You can do the math and see, and it's fine. So no big deal. All right, so when that's all done, when you go through all the conversion cycles, then you get an end of conversion. Then the value in your SAR is then dumped into the this final result register, and it's either justified left or right, and you're done. And then your program needs to go in, read this value, and then start another conversion if it wants. Now you can drive this with an interrupt routine if you want to, or you can just drive it with your code. In many of the chips, even in this family and many other micros, have more advanced A to D modules that will actually scan. You can select channels to be scanned, and it'll automatically go through a scan routine. You can have it take 4, 8, 12, 16, 32 signals and average them for you and give you an average signal of 16, 32, 8, whatever. And it can actually take 2 signals and subtract them and then interrupt you if there's a difference that exceeds an upper and lower threshold that you've set. So some of these modules are pretty fancy and they can do all sorts of cool things. This one's pretty dumb. It doesn't have those kinds of fancy characteristics. But still, it works pretty well. And for signals that are not changing very rapidly, it can be very accurate. And you can average it yourself. Just read in 10 values and then do the average, divide by 10, or better yet, read in a power of 2 and shift it. Yeah? So
what happens when your signal is changing very rapidly and your capacitor is changing charge in the middle of it?
So you are band limited. So there are frequency components that will exceed the capability of this chip. Anything over about 1 or 2 kilohertz will probably do that. And then what happens is, according to Nyquist, that sampling will be folded back in. You'll see an alias signal that'll be folded back into the frequency range, the bandwidth you can measure, and it will fool you into thinking that you're actually seeing the signal when actually you're not. You're seeing an aliased signal. So normally, to prevent that, you must filter the input. So not only do we have to put a little op amp to condition our signal, but often we need to put an input filter. And then there's some other things. We have to be careful about what's the output impedance of our sensor. If the output impedance of our sensor is very high, it may slow down driving current into that sampling capacitor and screw up, cause additional problems with our bandwidth. So again, that's why we want to condition it, because the output impedance of an op amp is very low. So that's a great way to condition that signal. So there are issues, and you do have to look at those things. There's also one of the other things. If you let's say you're sampling a signal pretty rapidly, but in the sampling process, there's a little bit of, we call it jitter, in how often you sample a signal. So let's say you sample it, you're sampling it pretty much at 1,000 hertz, but there's kind of a little warble on that 1,000 hertz, so that you're not, so sometimes you're sampling, 998 hertz and then 1,002 hertz. Well, then you're actually modulating the frequency, modulating the signal you're trying to capture with this jitter signal. So you have to subtract that off or somehow deal with that. And that's one of the reasons why the latency on the response time for interrupts is so important. We don't want interrupts taking variable amounts of time to execute. We want them to be very fixed so that we don't introduce all this extraneous jitter signal into the things we're trying to sample, especially when we're trying to go, a little higher frequency. And then for digital signal processing chips that are running, at video levels, those become huge, big deals. And they spend a lot of engineering activity getting the jitter out of their sampling and their jitter out of their latencies for interrupt responses and things like that. So there's a lot to this. It's not super simple. But if all you want to do is measure the value on a moisture sensor sticking in your farmer's field, this will handle that just fine. But if, on the other hand, you want to process video and put characters, insert streaming, streaming characters in the bottom of a video signal, you're going to need a little more horsepower than this chip has for sure. But you can do it. You just need a better So, yeah. So here are the things you have to configure. You have to decide what pin you're going to use to bring in your signal. You're going to, and so you want to set that up. And then, are you going to use some internal signals? Then you have to decide if you're going to, what you're going to use for your reference. Are you going to use one of the fixed voltage references to make your math a little easier? Are you going to use an external reference signal? Are you just going to use the ground and VDD that's on the chip? How's that going to work? Are you going to condition your raw signal so it fits nicely into your range? Or are you just going to have a bad mismatch and be wasting a lot of the resolution of your A to D converter? If you're going from 0 to 5 volts on your chip, but your signal only goes from 0 to 1.5 volts, then you're never going to use the 1.5 volts to 5 volts part of your range. So you're really reducing the resolution on that 1.5 volts you are measuring. But maybe that's okay. Maybe you don't need that precision. And then how are you going to drive the clock source? And you want to give it as fast a clock as you can, but you don't want it too fast. So your oscillator, as you change your FOS, you may have to adjust the conversion clock source that you're choosing to get it in the proper range so it does a quick but still not too fast conversion. You can't sample it. It has to run at about 1 megahertz maximum clock speed. So for our 4 megahertz clock, we have to do FOS divided by 4 to make it work. And then, are you going to use interrupts, and how are you going to format the result? When you use C, you almost always want to write justify it. But when you use assembly, a lot of times you want to left justify it, throw away the least significant 2 bits, and only use 8-bit values. And here's kind of a table. This is your clock speed, 32 megahertz processor, 20, 16, 8, 4. And you can see at 4, if we do FOS divided by 4, it gets us into this maximum sample rate of 1 microsecond. So that's what we want to do. And so you want to be 1, 2, or 4 microseconds. If you're down in the gray, you could go faster. You're wasting your time. And here you're trying to go too fast, and you won't get a good conversion. It'll be erroneous. And here's how it works. Set to go bit. Holding capacitor is disconnected after 100 nanoseconds. Conversion starts. You go through the bits. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and then you're done. Stored in the 2 result registers.